So let's just go over this real quick again. Here was the, here's kind of the riddle. You know, we've got force of gravity. And force of gravity is different based on the mass of the object. So if we have a big, heavy book, like my astronomy textbook, which we don't use in astronomy class, but it is very heavy, so it's got a large force of gravity. I also have a crumpled up piece of paper. It has a force of gravity that is much smaller, because it's just a single piece of paper. So force of gravity is going to be smaller here. Yet, we know that if we drop these two objects, they will hit the ground at the exact same time. Whether it's on this table, whether it's on the floor beneath us, they hit the ground at the same time. Boy, that was loud. The same thing would be true if we dropped them from the roof of the school. So the question is, how is it possible that these objects can hit the ground at the same time when one clearly has a bigger force than the other? Force should be proportional to acceleration. So if this has a bigger force, it should have a bigger acceleration. It would be speeding up faster, so it would hit the ground faster, you'd think. Well, let me just kind of clear this up for you real quick. We got to know exactly what acceleration is to figure out this little conundrum. F equals ma. Does that sound familiar?
Yes.
Yeah. So what does A equal then? Yeah, force over mass. More specifically, the force we're looking at here is force of gravity. Now, if I increase my mass, what happens to my force of gravity? It increases too. So if I have a small mass, I'm going to have a small force of gravity. If I have a big mass, I'm going to have a big force of gravity. They both go up at the same rate. So as they increase, that increase cancels each other out. In the end, if you are on Earth and you have a certain mass and a certain force of gravity and you divide the two like this, you're going to get 9.8 meters per second regardless of the mass, regardless of the force of gravity, and that's why they hit the ground at the same time. Without air resistance, both of these objects will indeed hit the ground at the exact same time. And you'll see an experiment. Well, you guys will. You won't, because I can't show a video on this. But there's a guy who actually went to a facility where they sucked all the air out of a big area, and they dropped a feather and a bowling ball from the same height, and they hit the ground at the exact same time. And you're going to see that live. Well, not live, but you'll see it on the screen shortly here. So yeah, that's what's going on. It all comes back to F equals ma. This might be the last time you really have to deal with F equals ma, so good for you on that. This chapter we are dealing mostly with projectile motion, which is objects that are in free fall or are moving in some sort of an arc or rolling off a table or something. And we'll get into the notes on that specifically tomorrow. But this is just kind of an introduction. All objects, whether they're heavy, whether they're light, will fall at that same rate of 9.8 meters per second squared as long as they're on Earth. And again, what this means is that you pick up 9.8 meters per second in speed every single second. After 1 second, you're moving at 9.8. After 2 seconds, you're moving at 19.6. After 3 seconds, you're moving at whatever 9.8 times 3 is. So you get the idea. That's the rate at which you're speeding up. So that's just kind of a little introduction to what we'll be doing as we go forward here.